Hi everyone, and welcome to week 5. The topic for today's lecture is causality, or how to establish whether one thing causes another thing using research. And this is important because most of research in criminology and criminal justice focuses on causation. There are some studies that look at the prevalence of different things or just generally describe the data, but a lot of what we try to do in crime and justice research is to understand what's causing different things. So what causes people to commit crimes? What causes people to support the police or be afraid of the police or, whatever the case is. So in order to establish causation, we're going to be looking at a couple of things. But first, I want to make a quick note that what we're talking about here is probabilistic causality. So if you say that one thing causes another thing, that can imply that every single time thing 1 happens, thing 2 happens. That's rarely the case in any kind of social science research. No matter what kind of cause you're looking at, it's rare that there's a one-to-one relationship between your cause and your effect. So instead, we're looking at something called probabilistic causality. Or does X, your cause, raise the probability of Y, your effect? In other words, does this thing raise the chances of somebody committing crimes? Does this thing increase the chances of someone having a particular set of attitudes towards the police? So when we talk about causality in this lecture, that's what I'm going to be talking about. And in order to establish causality, 3 criteria must be met. And we'll go through what these are, give an example, and then talk about how we actually do this in research. One of the criteria is that X and Y must vary together, or they must be correlated. In other words, as X changes, Y must also change. As you see changes in your cause, or as your cause happens, your effect must also be observed at the same time. Your cause must come before your effect. So X must come before Y. This one's pretty simple, but if your effect comes before your cause, you have a problem. And finally, we have to establish that the correlation between X and Y can't be explained by some other factor Z. In other words, this relationship that we're seeing between your cause and your effect, we have to be able to establish that it's not caused by something else. And so we'll talk about what that means as well. But first, I want to give you an example that I think makes these ideas a little bit more concrete. And the great thing about babies is that they're always learning about the world, and so they have to engage in their own kind of research. And these pictures are of my son when he was 1 year old. He's 3 now, but he learned how to use a clicker when he was 1 to turn the TV on. And I watched him go through each of these different stages to figure out that pressing the power button on the clicker causes the TV to turn on. So we're going to call our cause pressing the power button on the clicker, and our effect the TV turning on. So we have our X and our Y here. And so we'll talk about the criteria that needed to be met in order for him to establish that pressing the power button on the clicker turns the TV on. So our first criteria here, are X and Y correlated? In other words, does the TV generally turn on when you press that power button? If those things are related, you would expect to see that with more presses of the power button, we'll see the TV do more things, so turn on more times. If there was no relationship whatsoever between pressing the power button and the TV turning on, we would be lacking that criteria. All right, does the TV turn on after the power button is pressed? So here we're talking about time order. If you saw the TV go on and then press the power button, that would be less of something that would show that turning on the TV happens when you press the power button. So you have to have that time order there. You press the power button and then the TV turns on. And final criteria, can you be sure that there isn't some other factor causing this relationship that you've observed? So you notice that the TV usually turns on after you press the power button. But did something else turn the TV on? Was it the cat? We have to be able to rule out other causes of turning the TV on when you press that power button. And so, over time, I think Jacob figured this out, and he learned that the TV usually went on when you pressed the power button. It always happened after he pressed the power button, and he could be pretty sure that it was the power button turning the TV on and not something else. So in going through all of that, he established that there is a causal relationship between pressing the power button and the TV turning on. I will say though that you can also think about this as a probabilistic relationship. Most of the time when you press that power button, the TV turns on. But if you're not pointing the clicker at the TV, it might not turn on, right? If the batteries in the clicker run out, it might not turn on. So what we're looking at is a relationship where X, pressing the power button, causes the probability of Y, the TV turning on, to increase. So when you press that power button, it's likely the TV will turn on, but it doesn't always have to happen. But we would still consider that a causal relationship. X is causing Y in this case. So I established those three criteria. Now we're going to look at each of them in depth and talk about how we usually think of them in a research context, starting with correlation. So correlation, as I mentioned before, is the idea that X and Y, your cause and your effect, are related to each other somehow. When X occurs, Y typically occurs as well. Or you might think of it in terms of an increase in X would be associated with an increase in Y or a decrease in Y. So we're going to start here by looking at statistical correlations. And this is not a statistics class, so this is going to be an overview, and I'm not going to expect you to be able to calculate anything or do anything numerically here, but you should be familiar with the concepts that I'm about to cover. So one way to look at correlations, or a relationship between two variables, is a statistical correlation. And a statistical correlation is a measure of association between two variables that can be summed up with one number or one statistic. And we usually call that statistic R, just means correlation. So a correlation can be positive or negative, and it ranges from 0 to 1. The valence of the correlation, so whether it's positive or negative, describes the relationship between the two variables. With a positive correlation, you have one variable that increases and another variable that increases with it. If you have a negative correlation, your one variable increases and your other variable decreases at the same time. And it can range from 0 to 1. The closer a correlation is to 1, the stronger the relationship between those variables is. So the more that you can be sure that as one variable increases, the other variable will increase as well. If it's a lower or weaker correlation, the two variables are less closely related to each other. So here's what that looks like. Starting on the left side here, we have a correlation of 1 that's positive. It's positive because we can see that whatever variable would be on the x-axis or horizontal axis, as you increase on that axis going towards the right, your dots go up, right? So they're increasing on the y-axis, whatever variable that would be. And we'd say that this is a strong correlation because it's a straight line. You can see that every time you get an increase on the x-axis, you get an increase on the y-axis as well. There's no point where you could see two dots that are at different spots on the x-axis that are on the same spot on the y-axis. And as we move towards the right here, you can see that we used to have more positive correlations, but the relationships between the variables become weaker and weaker. So the dots become more and more scattered around that line. That means that as one variable increases, the other variable also increases, but it doesn't increase in sort of a one-to-one way. There's a little bit more fudge room there in that line that you can see. When you look at the no correlation graph in the middle, it shows that there's no relationship whatsoever between the variables. As your score on the x-axis increases, there's no observable pattern in terms of what happens to your score on the y-axis. Those dots are just scattered all around. Looking at negative correlations now, you can see the same thing happening, except the difference is that the line is in a negative direction. So as your score on one variable increases, your score on the other variable decreases. The higher the number of the correlation, the more you're looking at a line. So the more it is that as one variable increases, you can be absolutely sure that the other one's going to decrease as well. And so in social science, it's very, very rare to find perfect correlations or even almost perfect correlations. But you can see them in some other areas. So this is just an example of what a perfect correlation would look like. We're looking at pressure on the x-axis and temperature on the y-axis. So physics tells us that as pressure increases, temperature also increases, and it does so in this very, very uniform and linear way. So we'd be looking at a positive correlation here, where as pressure, your variable, increases, temperature, your other variable, also increases. And it's a correlation of 0.9989, if you can read that little text there. And that tells you that this is a very, very strong relationship. In other words, you can be really, really sure that as pressure increases, your temperature for any particular observation is also going to be higher as well. And yeah, that just says R is 0.999999. So if we were trying to establish causation, you might think that what you need is a perfect correlation, but that's not the case. And in order to establish causation in research, the only thing that you need to do is establish that there is some kind of correlation between the variables. But it doesn't need to be a perfect one-to-one correlation like we just saw on that slide. All you need to be able to show is that as one variable increases, the other variable tends to either go up or go down as well. So there's some sort of relationship in terms of what's happening with your one variable and your other variable. So we're going to go through some scenarios here that we're going to see, can we still establish causation if we have correlations that look like this? So we're going to say, what if your variable x is only weakly or moderately correlated with your variable y? In other words, if you were to put it in a scatter plot like that, it would look like a really, really fuzzy blob around that line. So let's look at this graph here. This graph comes from a survey that I did a couple years back. And this is looking at a pretty well-established relationship in the criminal justice literature. As police procedural justice increases, so as people's perceptions of how polite and fair police were increase, which you can see on the x-axis there, their perceptions of the legitimacy of the police tend to increase as well. So you have two variables. Your cause is thought to be procedural justice, the better police act, and your effect is thought to be legitimacy. So the more people view the police as trustworthy and deserving of obedience and so on. So what we see here is that we have a pretty strong correlation between x and y, but it's not perfect by any means. But the further along you get on the x-axis, so the higher scores on procedural justice, the higher scores on legitimacy tend to be. We can also see another graph here, which my head's going to be covering the actual correlation, but the PowerPoint will be posted, where it's looking at two different variables. And here the variables are people's scores on a scale measuring racism and people's support for punitive criminal justice policies. And here the correlation is around 0.5. So you can see on the scatter plot there that it looks a bit more fuzzier. It's less clear that there's that line going in any particular direction, but if you squint, you can kind of see that there's a positive relationship. So as people express more racism, they also tend to be more supportive of punitive criminal justice policies. And this is another really well-established finding in criminal justice research. So the question here is, can we still say that there's a causal relationship between these two things if we're not looking at a perfect correlation? So even though you have some people who view the police as really procedural just but not legitimate, even though you have some people who, express very low racism but are still very punitive, right? So you have people who don't quite fit on that line. Can we still say that there's a causal relationship here? And the answer is a really simple yes. So in establishing correlation as part of a criteria for causation, it doesn't have to be a perfect relationship. We're just saying that as one variable changes or takes on different values, the other variable tends to do so as well. But it doesn't have to be a perfect one-to-one relationship. So it still counts. Sometimes you also see a situation where two variables are related, but only under certain conditions. And we call these conditional relationships. So in other words, what happens if your correlation is only present under some conditions? And an example that I'm going to give here is also based on the racism and punitiveness measures. But these two graphs are for people who identify strongly as conservatives and people who identify strongly as liberals. And what you can see in the graph on the left is that for people who identify as conservatives, there is a really, really weak relationship between racist views and punitive criminal justice policies. So in other words, kind of no matter how racist a conservative is, they tend to have the same punitive policy views. If you look at liberals, on the other hand, racism is supported with more support for punitive criminal justice policies. And my head is covering the correlation again, but it's pretty high. I think it's 0.5 or 0.6. And so what you can see in that graph is that you do see that upward trend again, even though most of the dots are concentrated on the left side and lower end of the graph. So there tends to be less racism and less punitive policy support overall. But there is that relationship where you can see that as scores on those things increase, they tend to increase together. Whereas on the other hand, conservatives tend to be generally supportive of punitive criminal justice policies, but that support doesn't really change much depending on how much racism they're expressing. So the takeaway here is that even if you only see a relationship between two variables under some conditions, you would still consider it a correlation. So the fact that we don't see this relationship between racism and punitive policy support among conservatives doesn't mean that there's not a correlation there. It just happens to be conditional on political views. So in other words, even if you only see a correlation under some conditions, you can still count it as a correlation and it still applies in establishing causality. You would just have to then, understand that it's only occurring under some conditions. When this happens, we call it moderation. And in this case, we would say that political ideology moderates the relationship between racism and punitive policy support. So when we're talking about a relationship only occurring under some conditions, we refer to it as moderation, and we call the variable that tells you where it occurs the moderating variable. But again, the key takeaway here is that when you're talking about establishing causation, it's possible to establish causation even if a relationship only occurs under some circumstances. All right, so that's all I'm going to say about correlation. It's okay if it's not a perfect correlation. It's okay if it only appears under some circumstances. You can still use that correlation as one of the criteria to establish causation. Next, we're going to talk about time order. And time order, I think, is relatively straightforward. If you're looking to establish that there's a cause and an effect, so one variable causing another variable, you need the cause to come before the effect. And there are a couple of ways to do this in practice. So with correlation in practice, you're usually looking at some statistical measure of whether two things are related, like we were just looking at. With time order, there isn't a statistical component, but usually you're looking at the design of the experiment itself, of the study itself, or some other things that we'll talk about in a second. But there are a couple of study designs that can definitively establish time order. One is an experiment and one is a quasi-experiment. I'm going to come back to both of these relatively soon, but for now I'm just going to say that in an experiment, you, the researcher, are assigning some sort of treatment, so some variable, to different members of your sample. So you can be sure that your assignment of the treatment is coming before your measurement of the effects of that treatment. So that's under your control as the researcher. In a quasi-experiment, you're not randomly assigning any sort of treatment, but usually you're looking at something that's happening in the world and measuring effects before and after. So the time element of that is often built into a quasi-experiment. So if you have something like that, you can establish time order because you know when the thing you're interested in happened, you know when your independent variable happened, and you can measure your dependent variable at a later time. If you're not looking at experimental research, there are also longitudinal studies that can help to establish time order. And a longitudinal study is a study that looks at something happening over time. There are trend studies that look at changes within a population over time. So for example, if you were looking at attitudes about marijuana legalization in the whole population, you could track how they're changing over time, and then you would have some information about what the time order of different things are. There are also cohort studies where you're looking at some particular group over time. So you might be interested in baby boomers, for example. What did baby boomers think of marijuana legalization back in the 60s? What did they think of it in the 70s? What did they think of it in the 80s? And so on. So you're looking at, in general, changes in one group or cohort of people over time. There are also panel studies, and panel studies are repeated data collection from the same people. So the difference here is that you might take a survey of 1,000 people, then in a year, survey them all again, then in another year, survey them all again. And you could have a panel with 2 time points, you could have a panel with 50 time points. But the idea here is that you're looking at some group and then you're looking at them again and again and again. So what's really important here is that there are ways to establish time order between your variables that can be built into the study itself. And this can be really, really helpful in establishing causation. Oftentimes, though, this isn't an option. And a lot of research that you see is cross-sectional. Cross-sectional means that you're looking at a study that's taking place at one point in time only. An example of this that's really common is a single survey. So you survey 1,000 people, you get your responses, and then that's it. That's your data, and you don't get any more. So that would be cross-sectional in the sense that you don't get to look at what's happening to people's attitudes over time. You don't have any sort of time order built into variables in terms of when they're assigned or when they occur and when you measure the outcome. You just have responses from one point in time. So if you're ever working with data like this, you have to think about time order in a slightly different way. One way just comes from theoretical plausibility. In other words, does it make any sense to consider the time order in one way versus another way? An example of this is the relationship between gender and offending. So it's pretty well established that men engage in more crime than women. And when we think about this theoretically, it makes sense that being male could make somebody offend more, but it seems pretty unlikely that offending is going to make somebody male. So here, even if you only had a cross-section of people and you were looking at the relationship between gender and offending behavior, you could be pretty sure, based only on that, that your causal direction, your time order is that, gender assignment comes first and offending behavior comes later. But I will note that that becomes trickier in a lot of different situations. So let's say we're talking about that relationship between procedural justice and legitimacy. So it could be that people who perceive the police as more polite and fair are more likely to trust them. But it could also be that people who trust the police or view them as more legitimate are more likely to view them as polite and fair. So in those cases, you're relying more heavily on whatever theory it is that you're working with. All right, so now onto the bullet point that I already popped up here, retrospective reports. And retrospective reports try to build in a time element into a cross-sectional study by asking about things that happened in the past. So if you're trying to use offending as a variable, you might ask people about what they did in the past year. Then you can put a date stamp on that, and you know that it would come before something that, if you ask somebody, what are you doing now? It can also be possible to rely on external records or data to get information about things that happened at different points in time. So an example would be to look at police reports or medical reports or something like that. So if you're trying to understand a relationship between somebody's offending behavior and some other outcome, you could potentially look at police records to see about their criminal justice contact prior to the survey or anything like that to get information from some other point in time. So what's key here with these last two is that when you're doing cross-sectional research, it can be helpful to try to get information from other points in time, however you can get them, in order to build some of that time ordering into your research. So that's all I was going to say about time order. As I said, most of that's pretty self-explanatory. The last thing that I'm going to talk about in this PowerPoint here is spuriousness. And if you recall from the beginning of this presentation, the third criteria for establishing causation is that the relationship between your cause and your effect can't be explained by some other variable. And what we refer to this sort of thing is spuriousness. We'll just pretend that didn't happen. So spuriousness. Spuriousness describes a relationship between variables when the following things are true. some variable z causes some other variable x. The same variable z also causes another variable y. This variable x does not actually cause this variable y, but x and y are going to appear to be correlated until you account for this third variable z. And you've probably heard the phrase that correlation is not causation, and this is often the reason why that's the case. So let's think about ice cream and shark attacks. It is a true statistical fact that ice cream consumption is correlated with attacks by sharks. Now, if correlation was the same thing as causation, we could definitely say that eating ice cream causes people to be attacked by sharks. Right? Maybe you're just a little heavier in the water, maybe the sharks are attracted to the sugar, and we could think of all sorts of reasons that eating ice cream could cause somebody to be attacked by a shark. But we'd be missing the fact that both of these things have a different common cause. And specifically, you've probably seen this example before. In places where there are higher temperatures, more beaches and so on, there are more people eating ice cream, and there are more people swimming and being attacked by sharks. So it's not necessarily that ice cream sales are causing people to be attacked by sharks, but rather that both of them tend to happen under the same conditions. So it looks like there's a relationship between them. And we would say that the correlation between ice cream sales or ice cream consumption and shark attacks is spurious. And there are a lot of examples of spuriousness out there. One spurious relationship is that the number of churches and the number of bars in a location are correlated. So you might think to yourself, is it that people like to drink after they go to church, or is it that, drinking makes people need church? Do we have a causal relationship here? Not necessarily. And what this diagram shows on the left side are, is it that churches cause bars or that bars cause churches? Or is it that some other variable, such as the number of people who live in a particular place, causes both the number of churches and the number of bars? So in other words, in places where you have more people, you have more churches and more bars. And in places where you have fewer people, you have fewer churches and fewer bars. So the number of churches is correlated with the number of bars, but it doesn't mean that there's a causal relationship between those things. And because we're looking at spuriousness here. Another one is that there's a relationship between traffic accidents and number of speeding tickets. Does this mean that getting tickets causes people to get into traffic accidents? Does it mean that getting into traffic accidents causes people to get speeding tickets? No, not necessarily. And instead, one variable that might cause this spurious relationship would be the amount of time you spend driving in a year. So more time on the road, you're more likely to get into an accident and you're more likely to get a speeding ticket. You could probably also add driving ability on here, right? So the worse you are as a driver, probably the more likely you are to get into an accident, and maybe the more likely you are to ignore traffic rules along the way. But the key here is that those two things, even though they would be related, so people who get into more accidents tend to have more speeding tickets, we would say that there's no causal relationship because that relationship is spurious. It's caused by some other third variable. And finally, a last one on here, there is a correlation between height and reading ability, I think. My head is covering it, but I'm going to say it's reading ability. So either way, the correlation between height and reading ability isn't causal. It isn't that being taller makes somebody better at math. It is the case that, at reading. It is the case that as kids get older, they tend to get better at reading, and they also tend to get taller. So there is a spurious relationship between height and reading ability, and that spurious relationship is caused by age, a third variable. Finally, I want to warn you to beware of Nicolas Cage. So there is a pretty strong correlation between the films that Nicolas Cage has appeared in and the number of people who drown by falling into a pool. There's also a pretty strong correlation between the number of films that Nicolas Cage appeared in and the number of people who died by being hit by sports equipment. And you might be sitting here and thinking, what is the third variable that could cause Nick Cage to appear in films and also cause drownings and also cause people to die by being hit with sports equipment? And so something to keep in mind also when you're thinking about correlations is that chance is a factor as well. So sometimes things are just related to each other by chance, which is what you might see here. But this is another good example of correlation not equaling causation. So in this case, your other explanation for why these two things are correlated is just pure random chance. So I'm going to put all this together now. We have these three criteria to establish causality in research. We need our two variables, our cause and our effect, to be related to each other. We need our cause to come before our effect. And we need to be able to rule out other explanations for our cause and our effect being related to each other. And I'm going to talk a little bit about how we can do that in different kinds of studies. And specifically, I'm going to talk about three kinds of quantitative research. One is experimental research, one is quasi-experimental research, and one is non-experimental research. And as an example, I'm going to use programs that have appeared in a lot of prisons where inmates have a chance to work with puppies or dogs and train them while in the prison. And it's supposed to have good outcomes, including improving mental health for inmates. So let's say we wanted to do a study to evaluate how well one of these programs is working. In experimental research, as I said on the last slide, you as the researcher are assigning a variable to one group of people and assigning a variable to another group of people. So our variable here, our cause, is going to be involvement in one of these programs. If you're doing an experiment, you're going to randomly assign some group of inmates to participate in a program and randomly assign some group of inmates to not participate in the program. Afterwards, you're going to measure your dependent variable, in other words, your effect, which we're going to say is the mental health of the inmates. You could also look at this question using a quasi-experimental study design. And quasi-experimental study designs are similar to experimental designs, except that instead of randomly assigning different people into each group, you're using some assignment that's happened some other way. So it could be that one prison has one of these programs and another prison doesn't have one of these programs. You haven't assigned anybody to be in any particular program, but you could look at outcomes in the prison with the program versus the prison without the program. Another example of a quasi-experimental study would be looking at mental health in a prison right before a program is implemented and mental health in a program right after it's implemented. So your groups are, inmates before it and inmates after it. You didn't randomly assign anybody right to different points in the timeline, but you can still compare your outcomes between the two groups. And then finally, non-experimental studies are any studies that don't have these qualities of comparing groups or assignment to random groups. So in this example, you might be looking at mental health outcomes among inmates who decided to participate in a program versus inmates who didn't decide to participate. So there's no random assignment into groups. There's no big event that's dividing people either into groups or dividing people with a sort of hard timeline. You're just looking at whether there's a relationship between participating in these programs and mental health outcomes. And this is a pretty brief overview of these different types of quantitative research. We will come back to experimental research and quasi-experimental research as their own topic. We'll also talk about different forms of non-experimental research later. But that's your quick overview just for thinking about causation in the context of these different study designs. And we're going to start with experiments. And specifically, we're going to talk about why experiments are considered the gold standard of causation research. If you want to establish that one thing causes another thing, you pretty much have to use an experiment. And the reason for this is that experiments allow you to check off each of those different criteria for establishing causality. The first criterion, as we talked about, is that you need to see whether X and Y, your independent and dependent variables, are correlated. In other words, using an experiment, you could ask whether inmates who are assigned to a puppy program have better mental health outcomes than inmates who are not assigned to that puppy program. If there's a difference between the two groups, we can establish that assignment to a puppy program, your X, is related to mental health outcomes, your Y. Experiments also allow you to be certain of time order. In this case, you'd be introducing the puppy program, to some group of people and measuring health outcomes afterwards. So you can be sure that the independent variable, the puppy program, is happening before the mental health outcomes that you're looking at. And finally, experiments allow you to rule out confounding variables. Because you are randomly assigning people to be in these different groups, you know that there's no difference between the groups other than involvement in the puppy program. And this is something else that we'll talk about in probably more detail than you want later, but for now, let's just say that experiments allow you to do this. And the reason, again, is that the random assignment into groups means that the only difference between your two groups is that one is involved in the program and one is not. So because of that, we can see whether there's a relationship between being in the puppy program and having better mental health. We can be certain of the time order because we know when the puppy program happened and we know when we're looking at mental health. And finally, we can be sure that there is no other variable that's causing members of our treatment and control groups to be different from each other than having been enrolled in our puppy program. So if you want to establish causation, you need an experiment. But let's look at our other options as well. So thinking about quasi-experiments. Quasi-experiments allow you to check off two of your three criteria. The first is whether X and Y vary together. So let's say that we're going to use a quasi-experiment that looks at mental health in a prison prior to the introduction of a puppy program and after the introduction of the puppy program. So maybe we know there's a puppy program coming, we're going to measure everybody's mental health beforehand, and then we're going to measure everybody's mental health after the program is implemented. And we could see whether there's a relationship between these things. So is there better mental health in a prison after this puppy program is implemented than before? If we answer yes to that question, we could say that there's a relationship between having a puppy program and mental health. We can also be certain of the time order. So here, our whole experimental or quasi-experimental design is based around time order. We are introducing this puppy program and we're measuring mental health afterwards and comparing it to what came before. So we know that the order of things is that we introduced the puppy program and then we saw some change in mental health compared to our baseline before that. But what quasi-experiments don't allow you to do is rule out confounding variables. So for example, if you're looking at mental health outcomes and comparing them to some baseline from before the program is implemented, you're going to run into a problem, which is that something else might have caused changes in mental health during that time. Maybe the prison got new management who decided to implement the puppy program, as well as a bunch of other things to help people and improve their mental health. And if that's the case, you can't really be sure that it was the puppy program as opposed to other counseling programs or whatever other things were implemented that caused the improvement in mental health. So you can see a change, you can be sure of the time order, but with a quasi-experiment, you can't rule out different confounding variables. If you're thinking about the other example of this where you're looking at one prison that implemented the program and one prison that didn't implement the program, you have a similar problem with the last one there. So it could be that the prison that implemented the program is just a better environment altogether and has more support for inmates and so on than the one that didn't implement the program. So there might be other things that are causing a difference in mental health that you can't necessarily assume that it's this program that's doing it. All right, and finally, looking at causality in non-experimental research. And so one thing that non-experimental research does allow you to do is see whether X and Y vary together. And as an example of this, as I mentioned before, we'll say we would look at whether inmates who voluntarily enrolled in this program have better mental health outcomes than inmates who don't voluntarily enroll in this program. So in other words, do inmates who sign up for the program have better mental health than inmates who don't? And we might see that there's a relationship between signing up for the program and having better mental health. So we could probably check off that box. But can we be certain of time order? Not necessarily. So for example, it may be in this case, if we're just looking at overall mental health and whether somebody signed up for the program, it might be that inmates who had better mental health to begin with were more likely to sign up for the program. They had more energy, they were more interested in learning, they were, sort of more engaged with things, and it could be that inmates who had worse mental health to begin with were simply less interested in the program. So we can't be sure that the program is affecting mental health, as opposed to mental health affecting involvement in the program. Again, the difference here is unless you're using some sort of longitudinal study where, say, you enroll a bunch of people in the program and then track them over the course of time. So that would be one way around this with a non-experimental study. And finally, with our third criteria here, we also can't rule out confounding variables if we're looking at non-experimental research. So in other words, you can't be sure that some other variable didn't cause both an increase in mental health and a willingness to sign up for the puppy program. So it may be that inmates who have more family support or support outside of the prison are more likely to have better mental health, and they're also more likely to be interested in engaging in some sort of experimental program like this. It could also be something like, time left on the clock, and that could affect whether somebody engages in the program and also what their mental health is. So in other words, with a study like this, you also can't rule out that some other variable caused people to sign up for the program or have better mental health. So because of this, non-experiments are generally your worst bet for establishing causation, because the only thing that they really, with 100% certainty, let you do is see whether there's some relationship between your cause and your effect. So that concludes the lecture that I have for you guys this week, and now I'll just briefly talk through what the activity is for this Thursday. So this week I assigned, in addition to the textbook chapter, a chapter from Freakonomics that makes the argument that an increase in abortions following the Roe v. Wade decision caused the big crime drop. And this is an argument that I think has gained popularity. A lot of people are aware of it. But as you'll see, there are some scholars who are more critical of it. So along with this PowerPoint, I'm uploading a pretty short critique by Steven Pinker, who's also a pretty famous scholar, regarding the causality in this argument. So did Roe v. Wade cause crime to drop? Well, we'll see. So I want you to read the chapter, read the short critique of it, and then tell me the following things. First of all, is this claim that they're making based on experimental, quasi-experimental, or non-experimental research? Second, is there evidence of a correlation between abortion rates and crime rates? So this is our first criteria for establishing causality. Is there evidence of the correct time order here? So do we have an increase in abortion rates that's happening before crime rates began to fall? And for this one, you're going to have to think a little bit about the age of people committing crimes and so on. And then finally, can we be sure that the association between abortion rates and crime rates is not spurious? So could there be any other thing that could have caused crime to drop other than this change in abortion rates? So consider these different arguments and then tell me, how much you buy the argument that abortions cause crime to drop. For this activity, you could answer each of those questions with a sentence or two. Some of you guys write really awesome detailed responses, but this is just a reminder that that's not necessary as a baseline. If you have a lot to say, that's great, but you won't be docked points for only writing a sentence or two for each question. The usual reminder, I'm looking here for effort and thoughtfulness and to kind of figure out, where clarifications are needed on my end. And so just think of it that way. And finally, responses to the activity will be posted, or should be posted by this Thursday, and then comments on 2 other students' responses should be posted by this Sunday. And that's all I've got for you this week, so have a great week, and you'll see me again.